Harvard reveals 3I Atlas is not natural after its latest unexplained acceleration.
Picture this. You're an astronomer scanning the quiet night sky when you spot a blur moving just off the ecliptic plane. Days later, it's confirmed. It's not a comet from our solar system at all, but an interstellar wanderer. Now, as October approaches, you see it flare into an eerie green, its chemistry refusing to match what the textbooks say. This is exactly what scientists experienced, how an otherworldly object turned into the brightest mystery of the year. Before we move on, please take a moment to subscribe to the channel and like the video. Imagine watching a comet drift across the night sky when, without warning, it begins to glow in a vivid green light. That sight would stop anyone in their tracks. Now here's the strange part. Comets from outside our solar system aren't supposed to behave this way. They usually pass by as small, dim objects that escape notice without sensitive telescopes. But 3I Atlas threw that rule out. As it drew closer to the sun, reports began circulating that its coma, the hazy envelope of gas around the nucleus, was taking on an emerald tint. Amateur astronomers compared it to the glow from ordinary solar system comets, but the more scientists studied it, the less normal it seemed. The green color caught attention because it is usually linked to a common molecule in solar system comets, diatomic carbon. When energized by sunlight, this carbon compound emits a specific green light. That's why so many of the brighter comets visible from Earth historically looked like greenish fuzzballs in the sky. But with 3I Atlas, attempts to confirm this signature in its spectrum didn't line up with expectations. Instruments capable of pulling apart the light couldn't easily match the glow to the standard molecules seen in local comets. It was as though the source of the green wasn't behaving like a familiar case of carbon excitation at all. For context, comets like 46P Virtanen and Lovejoy both put on green displays that became public favorites. Their spectra proved the emission was exactly what scientists expected: carbon molecules energizing under the sun's ultraviolet light. In comparison, 3I Atlas didn't show a clear confirmation of those markers, leaving researchers puzzled. On paper, it looked like it might be acting like those green comets, but in practice, nothing lined up in a simple way. The match that should have been there just wasn't there. Some coverage went further and suggested that another chemical could be involved. Live Science noted that cyanide gas, which can also emit green under solar radiation, might explain what was being seen. The possibility of cyanide chemistry raised the stakes, because that compound doesn't usually dominate in the same way, nor does it fit neatly into our catalog of predictable cometary gases. Linking cyanide to an interstellar body added a whole new twist, because it called back to theories about complex organic building molecules hitching rides on comets during planetary formation. A hint of it appearing in 3I Atlas only made people wonder about what kind of chemical environment gave rise to this visitor in the first place. This unexpected behavior fueled speculation beyond the scientific community. When people heard the word cyanide or saw shifting colors in press images, the comparisons to alien probes or artificial objects spread online. In truth, color changes in comets are tied to chemistry and temperature shifts, especially as sunlight grows stronger near perihelion. But in this case, the dramatic shift made it easy for the public to imagine technology where scientists were instead looking for new forms of chemistry. Heat from the sun undeniably played a role. The closer 3I Atlas got, the more likely volatile gases could sublimate and spark reactions. Yet the exact combination responsible stayed unidentified, and the transient hues added to a sense of mystery. Think about the implications here. Every time a comet brightens, fades, or shifts in color, it's a signal about the molecules escaping from its body. A typical comet will stay within familiar ranges that match known compounds. In the case of 3I Atlas, the absence of a straightforward explanation made it stand out. Was this glow caused by an exotic mixture of gases never before tested by sunlight? Or was it a process that seems alien simply because we've only studied comets born within our own solar system? By the time debates cooled, one thing was clear. The glow from 3I Atlas didn't behave like the cataloged comets tracked for centuries. Its specific changes marked it as chemically unusual, belonging to a class of its own. This was more than just another green comet. It was a signal that interstellar ices may carry hidden surprises. And if its color seemed strange enough, the direction of its plume raised even bigger questions. Comets are supposed to behave in predictable ways, and one of the simplest rules is that their tails always extend away from the sun. The reason is straightforward: the force of sunlight and the constant stream of charged particles known as the solar wind push material outward. But when astronomers tracked 3I Atlas using the Hubble Space Telescope and the Gemini Observatory, they noticed something that broke that rule. Instead of its gas and dust flowing outward as expected, a distinct plume could be seen projecting toward the sun itself, like smoke drifting against the wind. That sight alone set off a cascade of questions among scientists and the public alike. To understand why this detail is so unusual, think about holding a lit match outdoors on a breezy day. Whatever direction you stand, the smoke coming off the flame will drift in the same direction that the wind blows. You would never expect the smoke to bend in the opposite way unless something else was forcing it there. Normally, a comet situation is almost identical. The wind in space is the steady pressure of solar photons and the particle stream from the sun. No matter how the comet turns, its dust tail points away. A second tail made of ionized gas can shift a bit depending on magnetic fields, but it too is driven outward. With 3I Atlas though, the physics refused to follow that reliable rule of thumb. As more data came in, researchers tried to make sense of what they were seeing. They ran trajectory models that attempted to simulate where the sunlight should drive the grains of dust and volatile gases. Time after time, the models failed unless an extra directed push was included in the equations. Without that addition, the plume oriented toward the sun could not be explained. The idea that something had to be producing a force strong enough to overcome solar radiation pressure was hard to ignore. Yet whether that force was natural or something more exotic remained wide open. For some observers, the sight of materials seemingly firing sunward was easy ammunition for claims of artificial origin. If an object in outer space shoots visible jets in a precise direction, it starts to look suspiciously like propulsion. But most astronauts and planetary scientists prefer a simpler idea: extreme outgassing. This is when pockets of gas trapped within the comet burst out powerfully enough to change both its appearance and its path. On ordinary comets, these eruptions tend to scatter material randomly or align with the heating of the surface. For 3I Atlas, however, the repeated pattern of a sun-pointing plume pushed the discussion into unfamiliar territory. Detailed modeling of the comet's trajectory produced what astronomers call residuals, small differences between predicted and observed motions. When those residuals lined up neatly with the direction of the plume, the conclusion was startling. The outflow of gas itself appeared to be exerting a measurable force on the object, altering its path just enough to stand out. It meant the comet was not only unusual in its appearance, but was behaving dynamically in a way that no model of standard comets fully captured. If you imagine a slow-moving spacecraft correcting its path with bursts from thrusters, the comparison was difficult to ignore, even if scientists insisted on natural reasoning. The wider impact of this finding was that it forced researchers to rethink how interstellar bodies behave when interacting with sunlight. A comet born in another planetary system may contain ices and materials that respond differently under solar heating. At speeds much higher than local comets, the sublimation of strange compounds could create directed plumes that go against everything we expect. In that case, the plume would be a product of chemistry and physics, not design. Still, to most people observing the data, the resemblance to propulsion remained an unavoidable thought. By the end of these studies, the majority leaned toward outgassing as the culprit for the sunward stream. They argued that rare combinations of volatile ices, paired with the comet's orientation, could generate jets strong enough to counter solar pressure. Yet, the phenomenon highlighted why 3I Atlas ALAS cannot be dismissed as just another comet. Its plume provided one of the clearest reasons why its motion looked engineered, even without evidence of artificial control. And while that debate was still ongoing, another set of observations was about to complicate the picture even further. The chemical fingerprints detected by the James Webb Space Telescope would bring even deeper surprises, shaking the questions about what this visitor was truly made of. How would you react if astronomers announced that a comet passing through our solar system seemed to carry chemistry that didn't match anything formed around our sun? That was the puzzle with 3I Atlas. When the James Webb Space Telescope examined it, the results showed something completely unexpected in its coma. The gas cloud surrounding the nucleus was made far more of carbon dioxide than water. That single fact was enough to send shockwaves through the community because, in our experience, comets almost always rely on water ice as their main component. Instead, this visitor looked like it came ready-made with a blueprint that belonged to an entirely different neighborhood of the galaxy. The scale of the imbalance was what caught researchers off guard. If you lined up measurements of different comets from across our solar system, nearly all of them fall into a relatively narrow band when you compare the amount of CO2 to water. Atlas, however, came in at a ratio about 8 times higher. That placed it far beyond the norms that anyone was used to seeing. What makes this so significant is that CO2 usually acts as a supplementary volatile in comets. It plays a supporting role in driving out gassing, but rarely dominates. In this case, it wasn't a supporting actor. It was the star of the show. Now tie this back to its strange glow and its disobedient plume structure. A comet releasing more carbon dioxide than water will naturally sublimate in a very different way. The gases expand, push through cracks at different rates, and react under the sun's radiation in ways that change visible colors. That may partly explain why the green tint appeared erratic, and why the plume of material jetted toward the sun. CO2 leaves the surface with momentum strong enough that, combined with unusual vents, it could drive material in directions we are not accustomed to modeling. The more scientists studied it, the clearer it became that composition and behavior were closely linked. And then came another surprise. Observations from the Very Large Telescope added a layer that no one was ready for: the robust detection of nickel vapor, but without evidence of iron. On comets inside our solar system, nickel and iron typically show up together in the gas spectra. The two metals are closely connected in how they are released from grains during heating. To find nickel floating without its usual partner was not just unusual, it was something astronomers had never encountered in open space before. When faced with it, they had to consider chemical reactions that don't normally occur at such distances from the sun. 3I Atlas reminded scientists that even natural objects can bring surprises big enough to challenge what we thought were universal rules. A comet shouldn't change colors so dramatically, shoot gas toward the sun, or carry chemistry that looks foreign to our solar system. Yet this one did all three. Its behavior shows us that interstellar visitors don't have to be artificial to feel alien. The mystery is still open, and the next traveler from outside our system could be just as strange. Keep an eye on future discoveries. How many other unexpected colors, plumes, and chemistries might be waiting for us?